So welcome everyone to my talk on QCSP monsters and the demise of the Chen Conjecture. This is QCSP in the sense of the quantified constraint satisfaction problem. And this is joint work with demise, who in fact did most of the work for this paper. But I'm going to present the work in a sort of historical context. And that's an area I've been involved in for many years. So let's begin with the constraint satisfaction problem. So the constraint satisfaction problem is a popular formalism in artificial intelligence in which one is given a triple, the variables, the domain, and the constraints, and in which one asks for an assignment of the variables to the domain that satisfies the constraints. And the most popular parameterization in the field of constraint satisfaction problems is where we fix the domain and we restrict the constraint language to be only from a certain set of relations. The interesting thing about the constraint satisfaction problem is it can be formulated in a number of ways. So one way is it can be formulated combinatorially. So you fix a right-hand structure C, which is the constraint language, and then you have an input left-hand structure A, and you ask whether there's a homomorphism from A to C, where a homomorphism is a mapping of the domain elements such that if you have a tuple in a relation in A, it's mapped to a tuple in a relation in C, but not necessarily the other way around. And then again, there's another formulation of the CSP as a model checking problem for a fragment of logic that just has exist and an equals, also known as primitive positive logic. So let's just very quickly see why they're the same. We can see that the pentagon, the 5 cycle, has a homomorphism to K3, the triangle. This is the problem. The CSP of K3 is graph 3 colorability. And we say that we can see that this 5 cycle has a homomorphism to the triangle if and only if this formula here is true on the triangle. And what we've done is we've mapped edges from the input pentagon to atoms in the sentence that we are testing on the triangle. So each of these edges is going to one of these atoms. So this is showing how the constraint satisfaction problem can be both combinatorial and logical. So the quantified constraint satisfaction problem is the generalization of the constraint satisfaction problem in its logical formulation by augmenting the logic with the for all quantifier. So now the sentence that we are trying to test on the fixed model has a universal, existential, and an equals. It doesn't actually matter very much for this problem whether you allow equals, because you can propagate out equalities. So I once said in a survey that the QCSP might be thought of as the dissolute younger brother of its better studied restriction, the CSP. CSPs are ubiquitous in computer science, while QCSPs cannot merely claim to be so important in applications. And I claim actually that there are 2 classes of sort of the most useful QCSPs, or QCSPs that are as useful as some CSPs. The first is when the domain is Boolean, so it's just true or false. It's like the propositional QCSP. And this is known as quantified Boolean formulas, or maybe as quantified SAT. And in fact, the complexity, computational complexity classification in this area is already known. There's known to be a dichotomy between P and P space. The other natural situation is when we allow relativization of both quantifiers. So for relativization of the exist quantifier, you can see we have exists x in S is the same as saying exists x s of x and. So that can be phrased as another CSP, as it were, because we have and in our logic. But we can't do the same with the universal quantifier because we end up getting negation in with implication there. So this relativized QCSP is in fact strictly different from the QCSP. It's not an instance of the QCSP. However, its complexity classification has also been solved. So what's left of the non-Boolean QCSP is a problem I believe to be mostly of interest to theorists. And I think that is more or less true, but I want to try to persuade you today that it still has a beautiful underlying mathematical theory, and that's why it's worthy of study. And it has actually, finite domain QCSPs have in fact been heavily studied in the literature and are known to reach complexities P, NP complete, and P space complete. The CSP can only reach complexities P and NP complete. So actually, I worked for many years on a whole collection of model checking problems based on restricting which of the quantifiers and connectives were allowed from first order logic. And many of these, when you then also restrict the constraint language, you can look at what computational complexities can be obtained. So the first thing you observe, let's look here at the CSP, the celebrated CSP, which we can consider as having the logic exists and or exists and equals. So for many years there was an open question about the computational complexity of these. I've even got it on this slide as a conjecture. It's no longer a conjecture. It was proved independently by Bulatov and Zhuk. And there is a split dichotomy between P and NP complete for exists and equals. So for example, for all and or and not equals, there would be a corresponding dichotomy between P and co-NP complete. So that's one of the areas we can solve. For it was obviously a difficult open question. There are many other fragments where it's quite easy to see a dichotomy or a simple classification. This case where we have both quantifiers and or, but not equality, which is much richer than when we also have equality, was also something I worked on, and there's a very interesting tetrachotomy there on the model checking problem between P, NP complete, co-NP complete, and P space complete. Actually, the only point on this whole slide where there is an open question is for the QCSP classification. And as I say, for many years we believed only P, NP complete, and P space complete could arise here because these were the only things that we observed. So my interest is very much in the interplay between logic and algebra. So I want to sort of begin with the idea of first order structures. There are relational structures and there are functional structures. The relational structures have a domain and then relations on them, and functional structures have a domain and then operations defined over them. We also call these functional structures algebras in the sense of universal algebra. And for me, the great interest in this area is the interplay between relational and functional structures. This is a quote, model theory equals logic plus universal algebra, from the first book on model theory, Chen Conjecture. I'm not sure whether everyone would agree with it in this day and age. Now let's bear in mind that all our structures are finite domain. The interplay that we talk about is this idea of operations preserving relations, or relations being invariant under operations. And what we do is we take tuples of the relations in row-wise, and we apply functions to them column-wise. And we ask here that when we have all these tuples in the relation, then the image under the function f is in the relation. So operations that preserve each of the relations of B are the polymorphisms of B, and the relations invariant under each operation of B are the invariants of B. And I use calligraphic notation for relational structures and blackboard notation for functional structures for algebras. So there's one side of a Galois correspondence that exists here. If B and B are both over the same finite domain, then the invariants of the polymorphisms of B are precisely the things that we can define with exists and equals in CSP logic, in primitive positive logic over B. There's actually one a Galois correspondence known for the QCSP as well, where we say the invariants of the surjective polymorphisms of B are precisely what can be defined over B with universal quantification, existential quantification, and an equals. Idempotent operations, so idempotency is the condition that the tuple of x's maps to x. These idempotent operations are obviously surjective. So if we restrict ourselves to the idempotent case, this is equivalent to when the constraint language has all constants added, then everything becomes surjective for free, and these two Galois correspondences coincide, as it were. The algebraic definition for QCSP, now we're parameterizing by an algebra, not a relation. It might have this form, so you would have a sentence phi of the QCSP logic written with atoms that are invariant under inv B, and then we would ask, is phi true over the relational structure with just those relations? Of course, we have a problem here as to what happens if the invariance of B is infinite. I mean, it is infinite, for sure it's infinite, because then we have a problem of how we encode relations. And there isn't actually a simple way to solve this. Traditionally, it's even forbidden. So if we want to study the constraint satisfaction problem of an algebra B, what we do is we study arbitrary finite subsets of inv B instead. So we use some kind of notion of compactness. So now I want to turn to a different topic, and I want to turn to something purely algebraic, and it's about the growth rate of generating sets for direct powers of algebras. So for an algebra A, a functional first order structure, we have a function over the natural numbers giving the cardinality of the minimal generating sets of the sequence A squared, A cubed. So if we go back a couple of slides, you could see, supposing these tuples here, these are m tuples, so this would be A to the m. If these tuples were in the generating set, then we could, using a function f from the algebra, generate this other tuple. This is the notion of generation that I'm talking about. And we would look at two particular cases where the cardinality of the minimal generating sets is at most polynomial, and we call that the PGP, or at least exponential, and we call that the EGP. Of course, it's not a priori obvious that there's nothing in between, because in principle we could have some kind of sub-exponential behavior. So the history of this these PGP and EGP, it goes back originally to groups. Well, groups are always PGP, but there still is some reasonably rich behavior in them. An old theorem classifies what happens for semigroups. If B is a monoid, then B has the linear PGP, otherwise B has the EGP. Now we can see the PGP very easily. I'm looking at this monoid with identity I, so you think of it multiplicatively. And plainly, from any tuple set that is of this form, all the ones I've got here, so we would have n instances of that one, n instances of that one, n, and then we'd have nm in total. From that we can generate anything, because we just choose for this B the first thing we want to generate, x1, x2, up to x whatever, k minus 1, xk, and then we can generate it. For the other part of the proof, what we argue is that if there is no identity, then this image of x over the domain must be smaller than the domain for every element x, because if it equaled the domain, there would be a permutation hidden in here, and a permutation generates an identity. So following this rule here, generalizing it to this rule, we find that a subset B of B to the n of size r can only generate r plus rn minus 1 to the n elements. So a generating set must be of this size. Remember, n is fixed, so this is at least exponential. So a particular type of PGP that I want to talk about today is this thing called, so a particular type of polynomially generated powers is this thing I want to call switchable. So if the generating set is a set of tuples that have this form, that when you read them left to right, the element only changes at most k times, obviously there's only a polynomial number of things that can have this form. Then if that forms a generating set, then we would say that we have the algebra is PGP switchable. So if that's a generating set, we have that the algebra is PGP switchable. And switchability, which is a related notion, was originally introduced not in the world of algebra, but in the study of quantified constraint satisfaction problems by Hubie Chen. And he gave a different definition of switchability that is based on reactive composition of adversaries. It's a more complicated definition. And he showed that when you have this notion of switchability, the corresponding QCSP drops in complexity from P-space complete to NP. And in a previous paper I've worked on, we can actually prove that these two types of switchability, the simple switchability that I've defined here and the more complicated type of switchability that Chen defined, are in fact interchangeable. So the big thing in QCSP for many years was the beautiful possible relationship between computational complexity and the PGP and the EGP. Chen conjectured in 2012 that if B was a finite relational structure expanded with all constants, then if the polymorphism algebra has the PGP, then QCSP B is in NP. Otherwise, QCSP B is P-space complete. And actually, a number of things have happened that really move us much closer to the Chen conjecture and seem to be suggesting more and more that it would be true. Zhuk proved in 2015 that there is indeed a dichotomy between PGP and EGP. And in fact, all of the PGP cases are witnessed by this thing we saw on a previous slide called PGP switchability. So that was a great step forward. And then a huge step forward was the resolution of the Feder-Vardy conjecture by independently by Bulatov and Zhuk. What they proved is that the constraint satisfaction problem is either in P or is in NP complete. I've given this thing the P case here with WNU, weak near unanimity polymorphism. You don't need to know what it is in the context of this talk. What that would have told you, given that there was this dichotomy between P and NP complete for the CSP, with the Chen conjecture, that would actually give a trichotomy for the QCSP between P, NP complete, and P-space complete. Essentially, the PGP cases would split between those that are in P and those that are NP complete. So the Chen conjecture seemed very approachable, and it seemed that we would be able to make progress in proving it. So this is the world in which the Chen conjecture exists. So if we have an idempotent algebra on a finite domain, if we can consider, so it's a finite domain, so if we consider two ways of encoding relations in the invariance of A, so one way is listing the tuples there, and another way is, say, in disjunctive normal form, but in propositional logic, maybe with constants 0 and 1. This is the Boolean not all equal relation, ternary not all equal relation, an NP hard relation. But what I think you can get a flavor of is it's much easier to write it in this logical notation, much more succinct than to write it in longhand in the tuple encoding. And so I've got a revision of the Chen conjecture where we use the DNF encoding. And I can prove then that if A satisfies the PGP, then the corresponding QCSP is in NP. Otherwise, it satisfies EGP, we know by Zhuk, and the corresponding QCSP is co-NP hard. This is a version of the Chen conjecture using infinite languages with the DNF encoding. So it deviates from some of the traditional encodings. What's interesting about it is it's a place in which the Chen conjecture is true, except we have co-NP hardness here, not a split between co-NP complete and P-space hardness. So another version of the Chen conjecture is essentially this version, but where we look at every finite redux. So we say if there's PGP, then every finite redux of the invariance is an NP. Otherwise, there is a finite redux so that the QCSP is co-NP hard. And in fact, this is equivalent to the revised Chen conjecture holding on the tuple encoding, and actually we know it's false. So let me just talk a little bit about the proof here of what's going on. Let's take A and B being strict subsets of A so that their union equals A. They don't have to have an intersection, but the most interesting case is when they do have an intersection. So if we think of 0, 1, and 2, that's a very interesting case where 2 is the intersection. 0, 2 is alpha and 1, 2 is beta. Zhuk proved that the EGP coincides with the situation where some disjunctive relation is PP definable. It's definable in the CSP logic. This is only in the idempotent case, by the way. And this here, what the row relation is it's a fuzzy equality. It's a fuzzy equality that doesn't care about the element in the intersection, the 2 that I've got there. And I could see that once you could define this disjunction of a fuzzy equality, you could define some kind of disjunction of a fuzzy ternary equality. And this ternary equality is the complement of some kind of not all equals relation. And of course, the not all equal relation is an NP hard relation. So once you can define something that's the complement of a conjunction of not all equals, which in this case is a disjunction of sort of ternary equals, then it's somehow clear that with universal quantification, you can hide a co-NP hard problem. But you have the problem that while this thing is guaranteed to be PP definable by the great theorem of Zhuk, we might not be able to write a specification of it in the logic of QCSP. It might be too big to compute this because we have to give it conjunctively because the QCSP is something that is a conjunctive object. But then I said, well, we're using this not the tuple encoding, we're using this DNF encoding. And that's where we are sort of cheating because this object does have a succinct DNF representation. It's easy to give. And that's why it works in this world. So I made a deal with the devil here to allow this strange encoding in order to make a place where the Chen conjecture was true. And actually the situation is a bit weird because when you allow only these Tor relations or even the sigma relations that we saw in a previous slide, you get a CSP that is already co-NP hard, obviously. We've seen that on the previous slide, but it's even in co-NP. So in fact, we saw for the first time QCSPs that are co-NP complete, but they're not real QCSPs because they have this infinite language and they're defined in the DNF encoding over propositional logic. They're not something real. In any case, this set of relations doesn't have a finite relational basis. It's not something that could ever be specified as a real QCSP. And it has this strange property that every finite subset is in fact in polynomial time, even in NL. And in fact, it's the language that refutes this thing that I mentioned before called the alternative Chen conjecture. So somehow strange things were happening because we made this decision to do something abhorrent. And the thing that we did that was abhorrent was allow this DNF encoding. So we still felt like the Chen conjecture should be true. There was a good chance of it being true. And the only thing needed to prove a weak form of it, at least say for co-NP hardness in place of p-space completeness, all we needed to do was give these polynomial computations of exist and an equals, or even for all exists and an equals definitions of Tor n from B. And this looked like a very approachable problem, a very doable problem. But unfortunately, Zhuk's work has destroyed the Chen conjecture in a number of ways. Firstly, there is a finite relational structure, even on domain size 3 that is has a QCSP that is co-NP complete. So they really do exist, these finite domain, finite signature co-NP complete QCSPs. None of these were found in natural problems. It really required careful looking to find them. It's a great surprise that this complexity class arises. Now, something even worse. Zhuk found finite structure on 3 elements. Again, that co-NP complete case was on 3 elements, where the corresponding algebra, the polymorphism algebra, has EGP, whereas the QCSP is in polynomial time. And so in this case, the Tor n are PP definable. They're definable even in the CSP logic, but their minimum size definitions are exponentially sized. So you can't use them in a polynomial reduction. So this is a great surprise. But it gets worse. Once the domain size goes above 3, then many strange complexity classes can arise. DP complete can arise. Even this strange class theta 2p complete. This is p with an oracle in NP, but you can only look a logarithmic number of times. So all of these different complexities can arise, and this is a great surprise because when we look back at how only simple complexities appeared in this table in all the other cases, it's a great surprise to imagine now very unusual complexities appearing at this point. So these monsters that Zhuk has created, this case, in fact, the isolation of theta p2 complete is first due to Emil Jarabek, and the first instance of a co-NP complete problem is actually due to Mirek Olszak. But the systematic study of this is mainly attributable to Zhuk. So in the paper, we actually proved that on domain size 3, only the cases PNP complete, co-NP complete, and p-space complete can arise. To get DP complete, we need to move to domain 4, and to get theta 2p complete, we have to move to a higher domain. And this proof and the way in which it shows these different complexity classes is very involved and is very complex. And it's for that reason that these complexity classes were not found beforehand, despite that much work was done on them. So the Chen conjecture has now succumbed. It's false. It's false in the strongest way, because there are even these EGP cases where the QCSP is in P. So that's a very strong contradiction to the Chen conjecture. And it's true only in this strange place. So it has its life in this strange place where we have relations encoded in propositional logic in DNF. That's a place where it's true, but it's false in what I call real life, where we just have finite constraint languages. Another place that it is true is when all unary relations are available as part of the constraint language, what we call a conservative place. So it's a natural large class on which the Chen conjecture holds. So there we do just have P, NP complete, and P space complete, and separated by PGP and EGP, and using the CSP dichotomy conjecture, the Fedor-Vardy conjecture proved by Bulatov and Zhuk. So the big open question is there any future in the Chen conjecture if we could modify it in the right way? So if we change the definition of PGP and EGP to something suitable, would it then make the Chen conjecture true?